Okay, in this lab, I'm going to look and study inertia. I'm going to use a modified Atwood machine. You'll see what that is in a second. We're going to study mass versus weight. We're going to look at net force. We're going to look at inertia and how mass affects inertia. We're going to use equations like F net, net force equals mass times acceleration. The force of gravity, or weight, is equal to mass times gravity. And then displacement equals initial velocity times time plus 1/2 acceleration times time squared. And we're going to use this one. We're going to modify it a bit so that we can solve for the acceleration in this lab on this Atwood machine, modified Atwood machine you're going to see. But to start off with, we're going to look at how mass and weight is different. If I have this 0.734 kilogram mass, which is our cart that we're going to use in the lab on Earth, versus if I had that same mass on the moon. Once again, I have a little friend that has a spaceship, so I got there and I was holding it up with the exact same hand, the exact same way. And when I did that, I could determine the mass because it doesn't change. Mass is just it's related to content, the atoms that make up that cart in this case, or whatever object it may be, and that's not going to change when you take it to the moon versus being on Earth. But now, when you think about weight, weight is a vector, whereas mass was a scalar. Weight is going to be a force in newtons. Once that Earth starts pulling on that object, like this cart in this scenario, well, it's going to be pulling this cart downwards, and I can calculate that weight by taking its mass, 0.734, multiplied by its gravity. We've seen it as acceleration due to gravity, but it could also be known as 9.8, not just meters per second squared. It's also known as 9.8 newtons per kilogram. So every kilogram of mass is going to bring in 9.8 newtons of force as a result. So, and then on the Earth, every kilogram of mass is going to bring in 1.6 newtons of force. When we're thinking about it in this equation, that mass is going to be turned into a weight, or a force of weight, force of gravity, which is weight, by multiplying it by the g. Okay, so do that. What's it? Calculate or maybe just know the mass and the weight of that cart, the 0.734 kilogram cart on Earth, where g is 9.8 meters per second squared, or on the moon of that same 0.734 kilogram massed cart on the moon, where g is 1.6 meters per second squared. So first of all, you should have got this. Mass is going to stay the same. It doesn't matter if you're on the moon or on Earth. It's still going to be the same cart. But weight, when we think about how we calculate weight, we have to take that mass and we got to multiply it by the g. So if the g is bigger, you're going to get more force, and it's going to be downwards because the planet's going to pull that object to the ground. Whereas the moon's going to pull that object to the ground. So we take the mass 0.734, multiply by the g, the 9.8, and we get 7.19 newtons of force, which is the weight of that cart on the Earth. On the moon, that's going to change once again because the g is going to be 1.6, so 0.734 kilograms times 1.6 meters per second squared, and we get 1.17 newtons. So significantly less force or weight on that object when you take it to the moon. Okay, let's look at just a scenario. We're going to look at this in the lab, and we're going to kind of compare the difference. If I double the net force while keeping the mass the same, how would that change acceleration? And so you may or may not have done this in class. You should have done it if you're in my class. But the rule of ones is you take the equivalent. So acceleration is equal to net force over m. So the equivalent of acceleration is just F net over m. And we put it over itself. But we compare it to the original, where 1 times anything is its original value. So when we do the math, we're going to double the net force, put a 2 in that place in the new situation. The mass is the same mass. We kept the mass the same. So it's going to get a 1 times. So this is 2 times. This is a 1 times. So 2 over 1 divided by, if everything was the same, the F net would be 1 times, or the same. And the mass would be 1 times, or the same. And when we do this, we don't get how much meters per second of acceleration we get. We just get that it's 2 times the acceleration. You get what you get out. What you put in, you get out, and you're putting in multipliers here, and so you're getting out a multiplier. With a little extra information, like knowing what the original acceleration, we could just multiply it by 2, and we can actually have the new acceleration. So that's the rule of ones. So this is a modified Atwood machine. we're going to have a hanging mass, which is going to provide, we're going to look at this as a system. When you think about this cart on the ground, there's going to be its weight pushing it down, but then the normal force of the ground pushing the cart back up is going to neutralize that. And when the system goes, it's going to be pulled by tension, which would be the same tension over here. But if we consider it as a system, we're going to ignore the internal forces. We're also going to ignore friction, which there'll probably be a slight bit of rolling friction. But the main thing is that we're going to get our net force from this hanging mass. Wherever this weight is pulling it down, the pulley is going to change that direction of that force from down to pulling on this cart to the right. If I clipped the string, the cart wouldn't move. But once with the string is not clipped and I let this thing go, the weight of the mass, hanging mass, M2 in this case, is going to pull the cart, and it's going to give it a net force and to the right. So we're going to kind of we'll just look at the cart when we're thinking about the system, what direction it's moving and how fast. We're going to start by having a hanging mass of 0.050 kilograms. If you've seen the masses, the mass sets, the main base is 50 grams, but divided by 1,000 is 0.050 kilograms. In order to get to newtons of weight, you have to have kilograms and not grams, so you'd always have to do a conversion if they gave you grams. But we're going to just figure out the weight. So how much newtons of force through the weight of this hanging mass are we going to have pulling on the cart? And it's going to be, when we do the calculations for weight, 0.49 newtons. Now, just looking at the cart, we're gonna not do much with the mass of the cart except for compare. I'm gonna start. We're gonna compare a few things. We're gonna study the effects of a greater net force on a similar mass. So we're gonna use this one cart, which has a 0.734 gram mass. It's not a hanging mass, so it's not gonna go into the acceleration. It's actually gonna go into the inertia, holding it back. Um, but we'll have the hanging mass that we detected before. The weight was 0.49 newtons of force. So we'll have a net force pulling this. And here's my lab setup. I went ahead and ran it. You'll see I'm actually going to go to have the cart go to the left instead of the right. We can watch that one more time. So the cart is accelerating from rest. It's going to travel a distance. So let's go back to this picture. This cart accelerates from rest, travels a distance. I make that distance. I recorded the time it took to go 0.5 meters. And so it goes from rest to whatever velocity, but we're not going to use velocity in the calculation. We're going to use time from an initial velocity over the displacement to find acceleration. Okay, so and this is just information. I used some timing apparatus, and I found out that the starting time, of course, was start, but was 0 seconds. The ending time, so this is going to be the time it took. The time it took to travel 0.5 meters was from rest. From rest, don't forget from rest. It's an acceleration equation. Took 1.5 seconds. So this is the information we have. Starting from rest, traveling 0.5 meters. Um, it took 1.5 seconds when I calculated that. We can solve for acceleration. You can rearrange this equation first. You can even put a 0 in for VI and cancel this first section out and solve for A. But I did it the way that a lot of students do it. Not always the best way, but it's the way I see students do it, just so you can follow the algebra. I went and did it in steps. So my displacement is that. I have my VIT. This is going to cancel out because it's times 0. I have the 1/2 1/2 times A times 1.5 squared. Notice what I did here. I got rid of the 0 times thing. I also put these together in front so I can have something A. And my next step is I'm going to multiply those values together. When I multiply them together, I get 0.5 equals 1.112 acceleration, A for acceleration. And I'm just going to put this A, I'm going to divide out the 1.125, and I'll just move that to the other side. So A equals 0.5 divided by 1.125. I get an acceleration of 0.444 meters per second squared. Okay, so this is something we're gonna compare to, because we had just the base, the 0.49 Newton force acting on that cart, causing that acceleration. So now we're gonna look at how is this acceleration gonna change. Oh, sorry. Let's go ahead and do one more thing. Let's how close is this to the theoretical value of acceleration? So this was a measured value in a lab, but this is the theoretical value, what it should be. We just take the F net equals ma equation, rearrange it for A, plug in some values, the net force that the object was being pulled by, and the mass that it had, and we calculate 0.667 meters per second squared. So that's actually significantly different than 0.444 meters per second squared. And so what may cause it to be different? Well, there's a few things. First of all, we ignored friction. The net force, there's going to be some backtracking of force, backwards force to contradict the force to the right. So net force would not be just equal to the mass. There's something you may learn later on. There's a little the string and the object. The pulley's not massless, so there's a little rotational inertia, and then there'll be more inertia just in the string going on. So there's a lot of things going on. Um, and then also, when we add a hanging mass, if we're considering this whole thing as a system, we really have to add everything together. So we're going to add a little bit of inertia by adding this extra mass. We're going to add the total mass is going to increase too. So that's going to be a resistance to the acceleration. Okay, now we're gonna go ahead. Our first thing is we want to test how changing that force affects the acceleration. So we're gonna go ahead and have two objects. We're gonna add another mass to this, so it's gonna double up its mass and therefore double up its weight. We can go ahead and do the same equation again. So now we're gonna have zero point 0.1 kilograms or 100 grams, but we want to have it in kilograms. 0.1 kilograms multiplied by 9.8 on Earth, and we get 0.98 newtons of force. So the weight of this is that's going to be pulling on the cart is going to be 0.98 newtons of force. Here's a video of that going on. And as you should expect, play it one more time, the cart goes a lot faster or accelerates quicker because you have more force pulling on it. So let's go ahead and figure out, starting from rest. I took a timer and I found out that it was exactly 1 second. To travel that 0.5 meters is exactly 1 second. So we're going to do the same calculation, but we now have a different number. We still start from rest. We still travel 0.5 meters, but we now do this in 1 second. So let's go ahead and plug in our numbers and do the math. With 0 times anything cancels out. We can put the 1/2 times the 1 squared together in the front. We can go ahead and just multiply that together, get that together. And we get 0.5 equals 0.5a, which of course, when you put that, a is equal to 0.5 divided by 0.5, you get a is equal to 1 meters per second squared. So the acceleration got a lot greater when we had more net force. Remember before, we had a net force, we had acceleration of 0.667 meters per second squared. Here we got an acceleration of 1 meters per second squared. And we doubled the force. We would expect double the acceleration, but once again, theoretical acceleration versus actual, because of all the factors like friction in the lab, are going to change it slightly. Okay, let's look at let's go back to having one single weight mass on it, back to 0.49 newtons. But this time we're going to go ahead and study the effects of having more mass being pulled. So not the hanging mass, but the actual blue cart. The way I'm going to do that is I'm going to put a cart on top of a cart. But let's see what doubling the mass, keeping the same net force should do to acceleration. Rule of ones, we put the equivalent over the equivalent. We plug in ones for everything that stays the same. The original, of course, stays the same, 1 over 1. And then, but the mass here, we double the mass. We're going to get 1/2 times the acceleration. What about tripling? Because we're going to see this in lab too. We're going to triple the mass. So I'm going to do that by adding 3 carts together. What do we triple the mass? Well, we're going to have the same net force in the new situation. We'll have the same hanging mass of 0.449 newtons. We're gonna have 3 times the mass because we're going to have 3 carts taped together, and versus the original, which is just 1 over 1. And so we're going to 1/3 times the acceleration. Let's go ahead and just kind of test it out and look at it. So here I have, once again, a single hanging mass. This is going to be comparing to the first experiment we did. But we have 2 carts, and we're going to go ahead, and what I do is I just tape those carts together. This is how I'm going to do it. I just tape them up together. And when I tape them up together, now they're going to have practically double the mass and therefore should have double the inertia. Inertia is directly related, or mass is directly related to inertia. So this is the lab being done. I go ahead and notice how much slower the rate of acceleration is. Let's play it one more time. As I'm adding more and more mass, it's accelerating at a lower rate over and over. This is the information I get from the lab. To travel the 0.5 meters from rest, it took 2 seconds now. So to figure out the acceleration, we're going to go back to this faithful equation we've been using. And now we have 2 seconds, and we're just going to plug in numbers. 0 times 2 is going to be 0, of course. That's going to, once just the same steps as I did before. You can do this better. You can rearrange the equation first and then plug in numbers. But for the sake of what I see a lot of students do and just thinking about math, this is three things multiplied by each other. So you can put the two things in the front, put the a in the back, and then now you can multiply those two together. So we get 0.5 equals 2a, and when we get our acceleration, we divide out the 2 from both sides. We get 0.25 meters per second squared. So now, with double the mass but the original net force, we're going to have 2.25 meters per second squared. Let's do one more thing. Let's go ahead and triple the mass. Might as well, since we did it before. Let's go ahead and let's just take, oh, I don't have my video of me tripling the mass, but I just taped one more piece on top of it. So let's go ahead and let's watch this go. Three masses stuck together, the same single hanging mass, the 0.49 newtons. And notice how much even slower the rate of acceleration is. Okay, love that video. Keep on watching it. Okay, now we look at, it took us, once again, we covered the same displacement. I used tape just to show you the beginning of this was the 0 point, the beginning of the tape. Really, the insides were a total of 0.5 meters, and that's what I took the time for. It took 2.5 seconds to get from the beginning from rest, a whole 0.5 meters, and that's enough information to solve for acceleration again. So we go back to our faithful equation, 0.5 meters. We didn't change the meters. We did have more time, but this cancels out. 1/2 times a times 2.5, that 2.5 squared. We put that in the front. We can go ahead and just 0.5 times 2.5 squared. Well, that gets 3.125 as the answer, as the preliminary answer for that part. And now we're going to take the 0.5, which was our displacement. We're going to divide out once again, we're going to divide out the 3.125. We get this, and I just flip sides. So when we solve for the acceleration, we get an acceleration of 0.16 meters per second squared. So more mass, as we add more and more mass, we get more and more inertia. So there's some finalizing, just questions that you have to answer. Think about what effect does increasing the net force have on acceleration. So that was changing the hanging mass's weight, was increasing the net force on the single cart. What did that do to the acceleration? Think about that. Look at the equation as you think. What effect does increasing the mass of the object have on acceleration? So this time we kept it the same net force, the single hanging weight. We weren't changing that, but we're doubling the cart. We're tripling the cart. What was that doing to the acceleration? So think back. Lastly, what do you do to increase the inertia of the cart? And what is the result? What would I have to change? Am I adding a cart or am I adding a hanging mass if I want to increase the inertia? And then the result of increasing the inertia, what's going to happen? Is it going to have more or less acceleration? And that's that.